For a methyl methacrylate monomer, you're given a viscosity at room temperature. You're doing a casting of this monomer. Typically, this monomers you cast for creating transparent plexiglass plates. It's also used for making contact lenses. You're given a circular channel, of length L. So it's a cylinder, 50 mm is a L, R is 2.5 millimeters, and Q is given as 2.5 into 10 power minus 4 meter cube per second. So you have to first look at the pressure drop for causing this monomer to flow through this channel and compare that with what happens when you instead push through a polymer made out of that monomer. So methyl methacrylate as a monomer is a liquid of low viscosity relatively. What is that viscosity? Right? It's given as 0.01 Pascal second. So if you knew the viscosity, you knew the flow rate, if you knew the length of the channel, and if you know the radius of the channel, you can compute delta P. In order to look at the viscosity of PMMA, which is not given, you will have to first estimate the shear rate from the flow rate and the radius terms, and then go back to the plot that we looked at to estimate viscosity, and then you can go ahead and for the same volumetric flow rate and for the same cylinder geometry, what the delta P is. Let's take a look at the solution in practice. Right? You know viscosity for the monomer, you know Q, you know L, and you know R. If you put these terms together, you will estimate that it's about 8 kilopascals roughly. You need to make sure that you convert all these terms to the same units in terms of meters for the dimensions over here in order to be able to get delta P in kilopascals. It's a very small amount of pressure drop. To take the same solution for PMMA, we have as data viscosity as a function of shear rate. So in order to find out what the viscosity, which is not given, it depends upon the shear rate that we are interested in. The shear rate can be computed from Q and R, and once you know the shear rate, you can, from this map for PMMA, decide what is the viscosity in this log plot. Once you estimate the viscosity, then you know Q, L, and R, and you can estimate delta P. You get it to be 24 megapascals, okay, compared to the 8 kilopascals. So about 4 orders of magnitude difference in terms of the delta P that is required. Okay, something to pay attention to about the differences between processing liquids and processing solids or high polymers. Where are these considerations important? Let's take a typical injection molding scenario where a plate like this with all these channels is getting molded. It turns out that during this, if you don't get the viscosity right, either by choosing an incorrect injection pressure or a melt temperature or a mold temperature, or not sure of what the geometry is, you can have premature freezing of the mold. That's called as a short. If you compensate for that by increasing the temperature and pressure and reducing the viscosity, you might end up making the material so fluid that it would open up the mold, and this region is called flashing. If you have filler in the polymer, you can then reduce the viscosity from the unfilled stage and increase it to a higher fill stage depending upon the amount of filler. But based on the shear applied, you could have powder binder separation or filler polymer separation. Sometimes, in addition to behaving like a viscous material, so as a pure fluid, it can also, the fluid, the polymer melt in this case, can also behave as a solid, an elastic material, right? Sort of like squeezing toothpaste out of a tube. So this particular material property is referred to as viscoelasticity. Viscous as a fluid, elastic as a solid. And so it behaves like a spring and has a lot of inertial force. And so this particular phenomenon is called jetting, and you can create a lot of defects based on voids over here. You can also have two regions of the melt flow freezing at a point, and you can have a well line. You could also have air traps where the air that is there in the mold cavity is not escaping because it's a tight fit, and so that should be a relief vent over here. In order to look at designing for injection molding, you have to combine materials and their properties with process conditions and also make adjustments to the part and mold geometry. These are iterative solutions, and so they are best computed using digital tools. PIM solver is an example of a tool where we started doing a lot of research about 15, 20 years ago and moved on to MoldX 3D and mold flow analysis over a period of time that capture material process geometry interactions, which is the basis of this entire course. So how are these decisions made on such a platform? So for instance, embedded in that are equations based on conservation of momentum, energy, and mass. And so these are then solved for specific material properties, specific geometries, and specific process conditions for a three-dimensional material. So viscosity, for instance, depends upon temperature and shear rate, as we saw. And so it is captured by an equation of this kind called a cross model, and an Arrhenius model captures the temperature-based interactions. Volume depends on temperature and pressure, similar to PV equals to nRT for an ideal gas. And so that can be captured by this modified Tate equation.